Okay, so today lecture is about the damped free vibration. In the previous lecture, we discussed about the undamped free vibration. So just to give you an overview of the previous lecture. So in the previous lecture, we discussed about the vibration or oscillatory motion. So we discuss different type of vibrations. That is free vibration and force vibration. We also discussed about damped and undamped vibration. And we also discussed about the degrees of freedom of the system. And in this course, we will only be dealing with 1 degree of freedom system. We also discuss about the periodic motion or simple harmonic motion. So simple harmonic motion is a simple form of periodic motion in which the response of a system can be represented by simple sine and cosine functions. So as you can see in this case here, the response of a system is represented by this sine function, and a here is the is this amplitude here. So as you can see, the x is just a sine function here, and then we can calculate the velocity and acceleration by just differentiating this displacement with respect to time. And as you can see here, that the velocity, which is this here, this plot here, is leading the displacement by 90 degrees, and similarly the acceleration, which is this line here, is leading the displacement by 180 degrees, and which we can also see in this figure here, or in equation here. Okay, so then in the previous lecture, we derived the equation of motion for undamped free vibration, which is you can see in this figure. So it is just the representation of an undamped system, which consists of a mass and a spring. And this is the free body diagram of this system here. So if you uh, displace this system from its equilibrium position, so at a distance x, so it will have spring force in the opposite direction to this displacement. So this is kx, and the weight is in the downward direction, and the normal force is in the upward direction. uh, and then we can write the equation of motion for this case, because the motion is only in the x direction. So therefore summation of all the forces in x direction equal max, so which is the Newton's second law. And then we can see that the x minus kx equal mx double dot. And then we can simplify this equation, and we can introduce this omega n, which is what we call is the natural frequency of a system, and which can be written as k divided by m under the root. Okay, now to solve this system, because we want to calculate the displacement from this equation here, and we know that this is a homogeneous equation because the right hand side is equal to 0. It's a linear equation because omega n is not a function of x. uh, and this is a second order equation because it involves the second differentiation of the x here. So from mathematics, we know that the solution of this system is just a sine omega nt plus b cos omega nt. Here a and b are two constant of integration, which we can calculate from the initial condition, that is it uh, t equal to 0, uh, x is equal to x1, and x dot is equal to v1. So these are our initial condition, that at time t is equal to 0. So x naught is equal to this x1, and x naught dot is equal to v1. So the velocity and displacement, if these are given, so we can calculate a and b, which in this case a become v1 divided by omega n, and b become x1. So we can write this equation in this form here. And finally, because this equation is a bit complicated, it involves both sine and cosine. So we can also represent this in this form here, which is a more simplified version. And in this equation, we now introducing two other constant c and phi, and c and phi is obviously can be related with a and b. And now we can just simply plot this curve here. And again, we can see that the time period is just 2 pi divided by omega n. Omega n here is the natural frequency, and t is the time period here. So if you just put the value of the omega n, which is k divided by m, so tau become 2 pi m by k under the root. And in addition to this, we also have this frequency, which is in the cycle per second. And this is what we call is the again the natural frequency of the system here. Now, if you plot this function here, this x with respect to omega nt. So if you plot omega nt on the x-axis and x on the y-axis, so you will see that this equation can be represented by this curve here, which is again a sine curve. But again, this is just a shifted sine curve because in addition to omega nt, we also have this pi here. So the pi will just shift the curve to this location here. And we can see that the distance from this origin to this point here is pi. And again, the distance from here to here is c sine pi. And the amplitude, which is from here to here, the distance is again c. And we can see that the one cycle is the distance from this position to this position here. So this is our one cycle, which is obviously equal to 2 pi radian, and which is omega n tau. So from here again we can calculate this tau here, which is tau is the time period. So this was the summary of the previous lecture, and you can watch the videos in full detail. So today's lecture is mainly about the damped free vibration. In the previous lecture, we ignored damping, but now we will include damping in our calculation. So as far as the damping is concerned, so first we will discuss different type of dampings that you can have in your practical engineering problems. So one is the viscous damping, one is the Coulomb or dry friction damping, and the third type of damping is what we call is the material damping or solid damping or hysteretic damping. We will discuss these in a minute. In addition to this, we will derive the equation of motion for the damped free vibration. Then we will solve the equation of motion, the same we did in the undamped free vibration case. And then we will represent these these graphically. And finally, we will solve some numerical examples. And just to again mention that we are following these 4 books. So some of the examples that you will see in the tutorial and also the theory is taken from these 4 books. Okay, so as far as the damping is concerned, so the damping is that in many practical systems, the vibration energy is gradually converted to heat or sound. Uh, while in the undamped case, we assume that there is no energy loss. So now due to reduction in energy, the response, which is, for example, the displacement of a system gradually decreases. And the mechanism by which the vibration energy is gradually converted into heat or sound is what we call is damping. And now a damper is a device which is assumed to have neither mass nor elasticity. And damping force exists only if there is a relative velocity between the two ends of the dampers. So okay, so it's typical to determine the cause of damping in practical system. So hence damping is modeled as one of the one or more of the following types. So in our case, we will model damping is either viscous damping. So viscous damping is, as you can see in this diagram here. So it's consists of a cylinder and a piston here, and there will be some fluid inside the cylinder. So when the piston will be moving in the fluid, and there are holes in the piston, so the fluid can move toward the both side of the piston. but when the piston will move, so there will be resistance to the motion, and uh, which will reduce the amplitude of the vibration. So when the mechanical system vibrate in a fluid medium such as air, gas, water, or oil, so inside this cylinder we can have one of these fluid. The resistance offered by the fluid to the moving body cause energy to be dissipated. So this will dissipate the energy of the system. The energy of the system will decrease with the motion here. Now another type of damping is Coulomb damping or dry friction damping. So here the damping force is constant in magnitude but opposite in direction to that of the motion of the vibrating body, and it is caused by friction between the rubbing surfaces that is either dry or having insufficient lubrication. So as you can see in this case here, so if we have a mass which is this block here and is moving on some dry surface, so obviously there will be a friction force, which is, you can represent this by mu n. N is the normal force, and then this friction force, which is opposite to the motion of the body, will dissipate the energy of the system, and this is also considered is one type of damping. Another type of damping is what we call is the material damping or solid damping or hysteretic damping. So this is the damping which is inside the material. So when a material is deformed, energy is absorbed and dissipated by the material. Um, and the effect is due to the friction between the internal planes, which slip or slide is the deformation take place. Now, the area of the loop in the stress strain plot denote the energy lost per unit volume of the body per cycle due to damping. Now, if the body is vibrating, so what will happen is that initially you are uh, applying load on the body, so you are applying load, and then after some time you are unloading the body, so the body is coming back here. So again, you can see that there is some permanent deformation. So the body is not following the initial path, but it's following this path here, and which you can see just the positive portion of this plot here. So this is our stress, and this is our strain, and we can see that the when the body is moving from A to B here, so the energy that you will apply on the system when you want to move it from A to B. So the total energy will be the area from A to B to D to C to A. This whole area from A, B, D, C, A. This whole area is will be the energy during the loading, but during the unloading. So this is the loading case, and in case of unloading, which is the BC. So when you unload the body from B, so it will just then follow this path here, and then the area under the curve is just this triangle here. So then the area of triangle CBD, and this is the unloading. So now we can see that the difference in the areas, that is EAB minus EBC. So this difference in the area is what we call is, which is this area inside the uh, you can call this area. So this red area is what we call is the area from A to B, and minus the area from B to C. So which is this area inside the loop, and this area inside the loop um, is the energy lost per unit volume of the body per cycle due to damping. But in this uh, course, we will only be considering the viscous damping. These are just introduced for your interest, but these are we will not include this in our calculation or numerical example. We will only include the case of viscous damping in our case. So now, if you consider this system here, so the dashboard, which is this thing here. So as you can see in this case, so we have this system. So now, in addition to the spring, we also now add this cylinder and piston here, and this is what we call is the a damper. So in this case, this is now the damped system, and if you vibrate this system here, so then the vibration will be termed as damp free vibration, because there is no force involved here. So once you give it a motion, and then you will let it to vibrate by its own. The dashpot or viscous damper is added to the system for the purpose of limiting or retarding the vibration. And in this case, it consists of a cylinder filled with a viscous fluid. So this there will be some fluid here, and the piston with holes or other passages by which the fluid can flow from one side to the other side of the piston. And simple dashpot arrangement, as shown schematically in figure, exert a force Fd. So this Fd is what we call is minus Cx dot. So this means that the force which is when the body will move. So this force of the damper is can be written as Fd equal to minus Cx dot, and minus because it's opposite to the velocity, and it is so this Fd, which is the damping force, is directly proportional to the velocity of the body. And now if we just put this constant here, and the negative sign here show that that it is opposite to the velocity here. So then this constant is this constant here, and whose magnitude is proportional to the velocity of the mass, as shown in the figure here. And again, you can see that this is the Fd, and this is the x dot or velocity. So then this force is just changing linearly with the velocity here. Now this c, which you can see here, is what we call is the constant of proportionality, and it is called is the viscous damping coefficient, and the unit of this is Newton second per meter. Now the direction of the damping force as applied to the mass is opposite to that of the velocity x dot, and thus the force on the mass is minus Cx dot. So we are using this minus sign here. Okay, so now we have now the free body diagram of the system here. So we have the mass, the weight is in the downward direction, the n is in the upward direction. We have one force of the spring, which is kx, and one force of the viscous damping, which is Cx dot. So now this is the free body diagram, so we can write the equation of motion. So obviously we will use this summation of all the forces along x-axis equal to max, and if we take this is our positive direction, because the x is in this direction, so x dot is also in this direction, and x double dot is also in this direction. We are assuming that everything is positive toward the right. So this means that we can write the equation of motion now. So minus kx, because it's to the left. Similarly, minus cx dot, which is again to the left, and equal to mx double dot here. We have this equation here. Okay, so now you can also simplify this equation, is that mx double dot plus cx dot plus kx equals 0. So this is the equation of motion for this case. In the previous case, for the undamped case, it was the same equation but without this Cx dot. Okay, so now in addition to this omega n, which we introduced in the previous case, here we will also introduce another constant, which is zeta. And zeta is equal to c divided by 2m omega n. So if we introduce this in this equation here, so you will see how this equation will change. So if we consider this equation here, And if you just divide this equation by m dot, so dividing by uh, so if you divide this by m, so then it will become x double dot plus c divided by m x dot plus k divided by mx equals 0. So this is the equation now here. Now, in addition to this, now we will multiply this c by m. We will multiply this with 2 omega n, and we will divide this by 2 omega n, just for simplicity. And then omega n square, because we know that this k by m is omega n square. We know this from the previous lecture. And x equal to 0. Now this term here, so if you just rearrange this term here, so which will become 2 c, and then 2m omega n, and then 2 omega n x dot and plus omega n square x equals 0. Okay, so now what we can see here, that this term here is c divided by 2m omega n. We can represent this by this zeta here. So if you just represent this by zeta, so the equation will become x double dot plus 2 zeta omega n x dot and plus omega n square x equal to 0. So this is the now the equation that we just simplify this equation, and it becomes this equation here. So in this this zeta is again a very important parameter here, and this is a non-dimensional parameter. So this means that it have no units, and zeta is called the viscous damping factor or damping ratio. And is called and is a measure of the severity of the damping. So it depends on the value of this zeta. So you will see this in a minute, that how this zeta affect the type of vibration. Okay, so now we have this equation here. So now we will we want to solve this equation. So to solve this equation here, okay, so if you just consider this equation here, so x double dot plus 2 zeta omega n x dot plus omega n square x equals 0. Now, in order to solve this equation, we assume solution of the form with unknown this lambda here. So we know this from mathematics, that if you want to solve this this differential equation, so you will assume that the solution is in this form here, lambda t. So this is the lambda is unknown, and a is again unknown here. Now what you will do here, that if x is equal to this one, so then you can calculate x dot, which will become a lambda e power lambda t, and similarly x double dot will become equal to a lambda square e power lambda t. So if you just put this x dot and x double dot in this equation here, so if you just substitute x dot and x double dot, so the equation will become lambda square plus 2 zeta omega n lambda plus omega n square and a e power lambda t equals 0. So this is the equation now that we get here. And now in this equation, because this term is the solution, so this means that this cannot be equal to 0, because this is the solution. So this means that if this cannot be equal to 0, so this means that this term is equal to 0. So this lambda square plus 2 zeta omega n lambda plus omega n square should be equal to 0. And this equation is what we call is the characteristic equation. So you may recognize this uh, from the mathematics that we derive this characteristic equation here. Now, because this equation is a quadratic equation, so it should have two roots, and we can calculate the roots by using this quadratic equation here. B square minus 4ac divided by 2a. So you can use this formula to calculate lambda 1 and lambda 2. So this equation should have two roots. So lambda 1 will become equal to, if you just use this equation here, so it will become omega n minus uh, zeta plus zeta square minus 1, and lambda 2 will become equal to omega n minus zeta minus zeta square minus 1. So now we have these two equations. So one is lambda 1, one is lambda 2. And these are the roots of this equation here. So now we know that the linear system have the property of superposition. So this means that the general solution is the sum of the individual solution, each of which correspond to one root of the characteristic equation here. So this means that x, so this x become equal to a e power lambda 1t, and then plus a lambda 2t. So this will be this equation of this solution of this system now. While if we just replace lambda 1 and lambda 2 by these values here, so then a will become equal to, so this one now become a1 and this become a2. So now these are two constant here. So this become equal to a1 e power minus lambda plus lambda square minus 1 omega nt, and plus a2 e power minus lambda square minus 1 under the root omega nt. So this is the solution of uh, this equation here. Okay, so if you just again write the solution here, so x is equal to a1 e power lambda 1 t plus a2 e lambda 2t, and then become equal to a1 e power okay. So we have now this solution here. Now as you can see here that the zeta, we know that the value of this zeta, because zeta is equal to c divided by 2m omega n. So this is the value of the zeta here, and we can see that this zeta, because c is always positive, m is always positive, omega n is always positive. So this means that this zeta, uh, the value of the zeta is always between 0 and infinity. So the 0 means that the system is undamped, and infinity means that it is the damping is very very high. So this is the range of this zeta here. And now the radicent, which is uh, this thing inside the under the root, which is zeta square minus 1, may be positive, negative, or even 0. So this means that if zeta is greater than 1, then this term will be equal to positive. If zeta is equal to 1, this term will be equal to 0. And if zeta is less than 1, but obviously it will be greater than 0, so then this term will be negative. uh, so giving rise to the following three categories of damping. So the first thing is that if now again, based on zeta, we can write the the motion is either overdamped. So if zeta is greater than 1, so the system will what we call is the overdamped system. And for overdamped system, uh, then you will have the so if the zeta is greater than so if zeta is greater than 1, so we know that the that this thing will be positive. And the roots a1 sorry the roots which is this from here, lambda 1 and lambda 2 are distinct real and negative numbers. It will be negative because a negative sign is here, and the motion is given by x approaches 0 for large value of time t. And there is no oscillation and therefore no period associated with the motion. And now you will see this in a minute. We will plot this graphically, that if zeta is greater than 1, you will see that if you um, give some motion to this overdamped system, it will not vibrate, but the vibration will just diminish over time. Another system is what we call is the critically damped system. And this is one zeta is equal to 1. So when zeta is equal to 1, this is what we call is the critically damped system. So when the system is critically damped, the roots lambda 1 and lambda 2 are equal real and negative numbers. Then this means that the roots, which is this root here, is lambda 1 and lambda 2, uh, is both equal to minus omega n. And the solution to the differential equation for the special case of equal roots is given by this. So we know that if the roots are equal, and because we know that lambda 1 is equal to omega n, so this was our lambda 1, which is minus 1, and then the lambda 2 was omega n. This was our lambda 1 and lambda 2. So if this term is equal to 1 here, so if this is equal to 1, so for this critically damped system, so lambda 1 will become equal to minus omega n, and similarly lambda 2 will be equal to minus omega n, because zeta is equal to 1. So then the roots are both equal and both negative. So we know that from our knowledge of the differential equation, that if we encounter this situation here, then what will happen is that the solution of the system will become equal to x a1 e power omega nt. So this is lambda 1 is omega n now, and then a2 and t here, and e power minus omega nt here. So here is compared to this case here. So it was a1 e lambda 1 t plus a2 e lambda 2 t. But because in this case the roots are the same, so therefore we will have to use this t here. And now the motion in this case also decay with x and approaching 0 for large t. And the motion is non-periodic. If the system is excited with an initial velocity or displacement or both, will approach equilibrium faster than even the overdamped system. Here zeta is equal to 1. So zeta is equal to cc divided by 2m omega n equal 1. So CC mean that the system is critically damped. So this viscous damping coefficient is we are just representing this by CC here. So and then zeta is equal to C divided by 2m omega n, which is equal to 1. So then CC will become equal to 2m omega n, and CC here is called is the critically damped coefficient here. Okay, so now in addition to this, now if you want to see how this um, overdamped and critically damped system will behave. So if you consider this system here consisting of K and C here, and if you give it some initial some sort of displacement here, so it will start to vibrate, but the vibration will decrease with time. And now we know that the response for both an overdamped and critically damped system to an initially displacement x naught and no initial velocity x naught dot is equal 0. So if you consider this case here, uh, so as you can see here that if you give it some initial displacement 30 here, so you can see that the overdamped system, so if you are using this parameter here, so m is equal to 1, so m is equal to 1 kilogram, k is equal to here 9, and c here is depend on the type of damping. So if you want the system to be overdamped, so you will use c to be 15, and if you use c equal to 6, so then the system become equal to the critically damped, and we know that zeta is equal to c divided by 2m omega n. So from here you can calculate zeta. So if for example if you use c is equal to 15, so if you want to calculate this zeta and you use here 15 divided by 2m, so m is 1, and then omega n, which is k divided by m, and obviously we know k and m, so we can calculate zeta here. That will become 2.5. This means that the system will be overdamped because zeta is greater than 1. And now for the second case, when we will use c is equal to 6 here, so 2 into 1 into k divided by m, and then it will become equal to 1. So this means that this is a critically damped system. And as you can see, the system is not vibrating, but the x is just decreasing with time, and if t is equal to infinity, so obviously then the x will become equal to 0. But in the critically damped system, as you can see, that it's approaching 0 faster than the overdamped system here. And now if you want to know how to derive this plot here, now because we know the for the overdamped system, we know the equation. So x was equal to a1 e lambda 1t plus a2 e lambda 2t, and we know lambda 1 and lambda 2 in term of this is lambda 1, which is you can calculate from omega n, and this zeta, and we can calculate zeta from here. So zeta is 2.5 in the overdamped case here in this example, and obviously you can calculate lambda 1 and lambda 2, and both will be different. So then you can calculate x dot. You can calculate x, which will be a1 e lambda 1t plus a2 e lambda 2t, and then from x you can calculate x dot by differentiating this x with respect to time. You will get this equation here, and now in this equation we have if you just differentiate this with respect to time, so it will become a1 lambda 1 e lambda 1 t plus a2 lambda 2 e lambda 2 t. So you will get this equation here, and now you have two equations, so x equation for x and equation for x dot. And now you just need to put the initial condition here. So the initial condition is that at t equals 0, x naught is equal to 30 or 0.03, and x naught dot is equal to 0. So these are the initial conditions. So if you put the initial condition in x and x dot, you will get this a1 and a2 in term of the lambda 1 and lambda 2, which is already so then you can plot this x, because if you know the lambda 1 and lambda 2 and a1 and a2, so you can just plot this with respect to time, and you will get this curve here. And similarly, you can plot this for the critically damped system, because for the critically damped system, if you remember, so the roots was both the same, lambda 1 and lambda 2 were equal to minus omega n. Then this x will become a1 plus a2t e minus omega nt. And now again, if you differentiate this equation with respect to time, so you will get velocity, which is this equation here. And now if you just put the initial condition, so you will get a1 is equal to this and a2 is equal to this. And then you can, if you know the value of a1, a2, and omega n, so then you can just plot this equation with respect to time, and you will get this curve here. So this is the how you will determine the response of the overdamped and critically damped system. Um, Now, in addition to this, now we will also need to discuss a case when zeta is less than 1, which is what we call is the underdamped system, which we will discuss next.